Hello, my name is Terry, and today I'll be presenting on our work for Wafer 2020, the surprising effectiveness of linear models in object pile manipulation. So before I go into the actual work, let me just motivate the problem. So um, manipulation is really hard, and I want to give an interesting example of this by what humans do in daily life, which is chopping and moving onion pieces around. So if you're coming from a traditional robotics perspective, most pipelines try to fix a priori what is my state that is governed by my physics. It could be generalized coordinates from Lagrangian dynamics or center mass coordinates, and for good reason, because once you have those states, it's easier to reason about how they evolve over time because you can derive the dynamics with Lagrangian, Newton order. But in this case, um, you could try that if you want, but the difficulty of observing what those states are, it's just immensely impractical. So from this single image, you have to think about what are the center of mass coordinates of all my onion pieces, and the cardinality of my state space is changing over time. And it becomes quite impractical. So we hypothesize that actually our internal human representation of this is fundamentally grounded in what we call output or observations, images, as opposed to thinking about the real complicated physics of collision and estimating their states. This problem is also interesting because it breaks some assumptions about traditional approaches that people have taken to vision-based manipulation. For example, a lot of single object manipulation pipelines rely on key points, which is hard to define here, or object-centric representations, which are again hard to define here. So we actually think a natural representation to use here is working directly in the space of images. So with that in mind, let me present our actual problem. So we have a camera looking at a top-down view of the board, and we call it the onion problem because it sounds catchy, but we actually decided to use piles of carrots because we can color filter them easier. It's an ongoing joke in the lab that they smell better. So given this kind of images and observations, our goal is to produce a policy that will stabilize the pile to this goal region into a desired target set. And we, throughout the presentation, will sort of provide a model-based solution. So what we're going to do is first we're going to establish a model of how our pixel dynamics are going to evolve. And using that model, we're going to find the best action in a simple policy. So I've told you that the space of pixels feels actually like a natural representation for this problem. And that's what we're exactly going to do. So we have sort of two representations that we have. The first one is sort of after color filtering and down sampling the image, we end up with this 32 by 32 grid. And that's going to be our representation of our observation. So I'm going to call that IK. And sometimes I'll choose to vectorize it into YK. It's right here. And we can also think about this as an object-centric representation. So we can take all of the coordinates that have non-zero pixels and just make a set of those points. And that's going to be my object-centric representation. And these aren't physical onion pieces or carrot pieces, but they're simply my pixels. So, excuse me, before I go into actually talking about the model, let's talk about our policy first, because that part is more intuitive to understand. So for the controller, I decided it's most natural to use a Lyapunov function for this kind of task. And what that is if I have a target set that is given to me, I can define a distance metric between a point and a set. Right? It's going to be what is the smallest distance I can define between my point and my set. And if I average all those distances for my current set of points, that's going to be my Lyapunov function for this task, at least in the particle representation. And to persuade you that it is, you should see that it's the sum of all distances, so it's always non-negative. And it's zero if and only if all the pieces, all the particles are inside the target set, and therefore um, all the distances are 0. Right? So it successfully encodes whether I have succeeded in my task or not. So now, if I want to extend this to images, it's quite simple to have a pre-computed distance matrix where what's inside each sort of pixel in that matrix corresponds to the distance between the target set and that point, that pixel. Right? So if I just think about that that D matrix as a measure, and I multiply that with my image, I can alternatively get my Lyapunov function that way. I just added the normalization term, assuming, what if I assume that the whole sum of images, well, all the carriers in the board are all the same throughout time, but I could sort of choose to leave out this term and make the Lyapunov function linear in terms of my image. So you should also think about this and persuade yourself that it's not negative, because both my measure and rework measure and my image is non-negative. And this is also 0 if and only if the non-zero indices of my image coincides with the 0 indices of my distance matrix. So assume that someone gives us our forward prediction model of an image. By the way, I've chosen to use first order here. So in general, this should be a history. But since I know that this phenomenon is quasi-static, it's kind of like a prior I chose to include in my model. So if I know that if I have that prediction, then I can predict, evaluate the Lyapunov function, and choose the best one that will drive me downhill. So in that sense, V here is a control Lyapunov function, right? If for all images that are not successful yet, I can always find an input that can drive me downhill in this Lyapunov landscape. And for most target sets, this seems to hold, because I can always find a small shared piece on the edge of the board that I can isolate and push towards the target in order to decrease the Lyapunov function. But we're going to say it's an assumption, because depending on the shape of the target set, it could be extremely non-convex, could be O, and the paddle width, the pusher width. We might not be able to achieve this. So we're going to assume that we can always drive this downhill. And then we're going to do a steepest descent for the controller for this Lyapunov function. So we're going to have some candidate views, project it forward using our model, evaluate the Lyapunov functions of all those features, and choose the best one that will drive me downhill. Right? And for our purposes, we kind of brute force this optimization on a set of grid of actions where our parameterization of action is the starting point of the paddle, the length of the push, and the angle. So now if we have a prediction model, we can sort of successfully drive it downhill. So the natural question to ask now is, how do we get the prediction model from data? And the first sort of choice we made was using a deep prediction model. So it's a typical deep learning model trained end to end. We have an image and an encoder. We have some dynamics layer going to a decoder. And we tried to train this with 23,000 samples and just on the prediction error. And over time, we found that it is possible to achieve a good loss curve and a good prediction error overall. But it kept frustrating us because the overall model didn't agree with some fundamental physical understanding that we have about the phenomenon, and that made us fail with the closed loop policy. For example, it would make carriers appear out of nowhere or make them disappear suddenly. So we have struggled this for a while, and then just thought about what if we could use a more principled model where parameter identification is easier, and we can sort of encode better our knowledge about what can be allowed in the phenomenon. So the model that we're going to look at is the Swiss linear model. So we're going to assume that the image-to-image translation, the dynamics, happens according to a linear map, and our action is going to be represented by choosing what that linear map is. So if you think about this, if we fix an action, The identification, the optimal identification of A from data is just the least squares regression problem, where because our vectorized images evolve linearly, I can just stack them up and solve the matrix least squares problem. And it's also straightforward to put in some kind of regularization conditions through constraints. So, for example, I could force my A matrix to be non-negative, and that's sort of encoding my prior that since both my images are positive, non-negative, my matrix should be non-negative as well. If I wanted to have a more mass conservation sort of a prior, then a column sum constraint is also natural to include. And if you think about the identification of a Markov chain, for example, if you think about the images in a Markov chain, it sort of approximately represents the constraint that the probability should sum up to 1. And similarly, it represents the constraint that the onions in the board, their mass should be approximately conserved. So, but it turns out if we solve this as a QP, the number of decision variables are a million, because Y, which is our vectorized images of 1024 size, so A is 1024 by 1024, and that's just too large to solve in a single QP. But if we can sort of throw away the column sum constraint and only worry about the non-negativity constraint, then it turns out we can decouple this problem row by row and solve 1024 QPs of size 1024 instead of solving a 1 QP of a million decision variables. So that's what we did. So we built up a head of simulation, we trained it over the same 23,000 data, and then the natural question to ask is, for the linear model, is there a better way to interpret the fact that our model has learned the right thing? And here's the representation that we came up with. Here's the method that we came up with. So if we think about what's happening in the linear map, the red pixel, so Y is the vectorized image, so each element represents a pixel. It's going to be a dot product of one row of A and the entire image of YK. And if we sort of turn that to image coordinates where YK becomes IK, I can also have the row of A be a similar image, and it's going to be like a kernel that's going to be multiplied with the whole image and then summed up together to predict, to create the red pixel right there. Right? So the whole linear map in terms of vectorized images can be represented as a tensor multiplication in the image space. So let's visualize what those kernels actually look like. Right? So just to remind you, what's happening here is that IK is being multiplied with the corresponding kernel. It's going to be, it's going to sum up all the resulting image, and then it's going to be put that value on the red pixel. So let me replay this. So outside the push area, you can see that it's always a linear map, identity map, right? So it's just one pixel right there, the kernel. So it's only choosing one pixel to put into the new red location, which makes sense because it's completely outside the push area. So the linear map is essentially predicting that nothing is going to happen to that area. But if we go, as we go near the edges of the push area, something interesting starts to happen, right? So it's actually learned the kernel. They'll multiply the swept area, add those together, and then put them in that location. It also predicts some spills, right, on the side of the area. And in the middle, it predicts nothing. It's completely zero because it's going to predict that things are going to be gone from that location. So this was a cool result because I was happy that I could interpret what that map is actually doing. It seems all right. And there's nothing funky going on, like onion pieces suddenly disappearing or appearing. So now, if I have a single U, I know how to identify an A matrix, but it's kind of time consuming to do that for every single U. So one trick that we came up with is by using the spatial structure of the push. So we're gonna, given the image and the push rectangle, we're gonna transform it into the pusher coordinates, apply our map, and transform it back So using this affine transformation, we can sort of inject structure to significantly reduce the amount of data that we need. So we only have different A matrices for different push lengths. And I think we have 5 discrete push lengths. Now, finally, as a baseline, we've also prepared an object-centric model. And what that does is we get away from images and actually think about the coordinates of these particles. And then, so we have a pusher, sort of the area that the pusher is swept by. We're going to take all of those coordinates. We're going to sort of just distribute them according to some uniform distribution at the front of the pushed area. And we actually took the true distribution, see what it looks like, and it seems like a uniform distribution is a pretty good approximation for the true distribution. So when we actually looked at the prediction error of the during the test, it seemed like surprisingly the linear model does extremely well. Here you see these are different regularization of the linear models that we made. So OLS is the ordinary least squares without any constraints. We added rich regression, Lyapunov regularization just to see what it does. And the non-negative least squares is the multiple QPs that we solved with the non-negative constraint. On the DVF models here, or the deep models, it's an acronym for Deep Visual Foresight, which is another sort of paper that tries to do image dynamics with deep models. The original model goes from image action to image, while the affine model, we've kind of gave it that same trick of affine transformations. So it's only learning image to image maps corresponding to a single push length. So surprisingly, non-negative least squares is showing the best performance in test data. And if we actually visualize the predictions, they're all visually plausible. Very nice. But still, quantitatively even, the switch linear model is able to achieve the least amount of test error with less parameters. And here is what's going on in closed loop. You can see that the linear model, the object-centric model, the DVF affine model is succeeding, but the DVF original model does not. And the reason for that is sometimes the deep models would hallucinate something like onion suddenly appearing or suddenly disappearing. And it would hallucinate something that it thinks is the best it can do to drive the Lyapunov function downwards. However, when it actually takes that action, it does nothing. It does nothing to affect the actual image. And the same image would get fed back again to the controller, and it just does the same thing over and over again, thinking it's going to make a change, but it doesn't. So looking at the Lyapunov descent curve, you can see that the switch linear model and the object-centric model are both doing okay. The DVF affine model usually takes a bit more iterations to complete the task, but it still completes it, while the original model fails. So these models were trained on sim, but we're just going to use it directly on the experiment to see how they generalize to new environments. And the experiment, we just have a typical setup of we have a camera, a KUKA arm, some pusher, cutting board, and we actually cut carefully finely for this task. So here's a showcase of our experiments. You can see that it's sped up, by the way, but it's successfully sort of driving this downwards. And it's also robust against discrete time, stable against disturbances. So here I have a ruler just trying to push those out, and it's able to sort of recover from these disturbances into collecting them onto a target set. So let's look at the results of different methods, different models. You can see that linear and object-centric on the left, 2 columns on the 2 rows are succeeding. But the DVF original is failing, as we saw on the sim. You can actually see what I was talking about. It's doing the same thing over and over again, expecting it to change, but it's not changing. But what is surprising here is DVF affine. It used to succeed in simulation, but now that we have moved the environment over to real, it's not succeeding anymore, which is very interesting. It's also having the same error, doing the same thing over and over again. So DVF affine, which used to do well on sim, now fails on the experiment, which tells us that it clearly overfit to the simulation environment, while the linear model was able to generalize to the real environment as well. And this tells us that linear models have some kind of a better inductive bias over deep models on how to predict the evolution of images for this task. So the big lesson here is really for a vast majority of tasks involving image dynamics or image predictions, perhaps sometimes we're too quick to jump onto neural networks, whereas maybe there are some cases where linear models also do well. And when they do well, they allow really good principled parameter identification, and we can regularize them based on our knowledge, while such regularization or debugging processes are much harder for the deep model. Well, thank you so much. As a last show, I have a model of my system drawing letters MIT, just to show that it's working on non-convex sets. All right, thank you so much.